In this video, we're going to go over impulse. So firstly, we'll study what is the equation for impulse and how it is related to momentum. In the next about a minute or so, we'll find out what are some conceptual applications of impulse. So how impulse relates to real life examples and how it is applicable to our real world life. And finally, in basically 2 to 3 minutes, we'll find out the step-by-step instruction, so a method for solving impulse-related problems. Finally, for the rest of the video, we're going to go over 2 examples where we'll see how our method applies to solving impulse-related problems. So let's take a look by firstly examining what is impulse. So impulse, which is often written as letter J, is equal to force times time. Another formula for impulse is final momentum minus the initial momentum. So impulse has 2 formulas essentially. Now, as you can see, we can also set force times time equals to change for the momentum. So this is very similar to work energy theorem, right? If you have already watched the video on that. Essentially, one significance of this equation is that it provides a link between the forces and the momentums, essentially these 2 big units in physics, right? Now, you might look at this and think, but wait, didn't we just learn that the momentum is conserved, right? That the initial momentum is equal to final momentum. Well, that is not always the case, right? Let's say you're driving in the car, right? You're driving at some sort of velocity, right? So you have some momentum, and then you stop, so your momentum is 0, right? Right there, your momentum wasn't conserved. And that is because you're applying some external force. In the example of a car, you're applying force of friction from the brakes in order to stop the car. So another kind of significance of this equation, what it tells us, is that you can change your momentum if you apply a force over some period of time, right? Let's take a look at some other conceptual applications of impulse, right? So I want us to note the thing is that the equation for the impulse, right, J is equal to force times time, that since force and time are basically on the same side of the equation, right, they are inversely related. So if you forgot what it means for 2 variables to be inversely related, what it means is that as I increase force, right, as I increase one variable, the time goes down. Or the other way around, as I increase the time, let's say, right, my force will go down. So it's pretty important to understand this relationship between force and time, right? The longer the time is, right, that you take between the interaction, the bigger the time is, the smaller is going to be the force. So how does it apply to real life examples? Well, for the fans of boxing, let me ask you this question. How does the punching glove reduce the force experiencing by the boxer? I know this might seem like a really obvious fact, but what is the actual physics behind it, right? Of course, it's related to impulse, right? The punching glove increases the time that it takes, right, for this punch to occur. Essentially, instead of happening at an instant, right, it takes some time for the glove to compress. So by increasing the time, you're decreasing the force experience, right? Similarly, the airbags in our cars work. So the second question is, how does an airbag in the car reduces the force experienced during the collision, right? The airbag increases the time it takes, right, for basically that the collision takes place, therefore reducing the force that you are experiencing during the collision. So now let's take a look at how we would solve quantitative problems, right? So our method is the following. It's almost the same as our method for conservation of momentum. We draw 2 separate diagrams to represent initial and final moments. In each diagram, we'll label masses and velocities if it is applicable, right? But we also have to label and identify the force. So introducing forces here is the new addition here. We'll calculate the initial and final momentums, right? And then essentially, instead of plugging into conservation of momentum formula, so initial momentum is equal to final, right? No more. We plug it into this formula. So for our force, final, and initial momentum. So let's take a look at how this method applies to these next two really quick problems. Over here, we have a soccer game. During a penalty kick in a soccer game, a goalkeeper saves a ball by stopping it with their hands. The soccer ball, with a mass of 0.43 kilograms, is initially traveling towards the goal at a speed of 25 meters per second. The goalkeeper stops the ball in 0.05 seconds. Find the force that he applies on the ball. So let's take a look here. So again, the impulse, right, force times time is going to be equal to change in momentum. Let me ask you this, right? What is going to be the initial and final momentum in this case? Because the force is obviously what we need to find, and the time is already given. So we need to find final and initial momentums. So initially, the ball is moving with a velocity of 25 meters per second. So it's m times this velocity that we're given. Final, however, momentum. The goalkeeper makes the ball stop, right? So therefore, the final momentum is 0, right? Because velocity is 0. So plugging this in, so 0 minus mv, right? Or we just basically plug in this. Dividing both sides then by t, we can calculate our final velocity. So negative 0.43 times the velocity over time, we have an answer of negative 250 newtons, and the negative sign here just indicates that the force that he applies, right, is opposite to the direction of motion. Great. So as you see, a pretty straightforward problem. Now let's take a look at the next example. It's going to be pretty similar to the previous one. So during a track and field event, a hurdler with a total mass of 60 kilograms is running at 8 meters per second towards the final hurdle. To clear the hurdle applies a force against the ground with her foot for 0.2 seconds, which increases her velocity to 10 meters per second. Calculate the force applied by the ground, right? Or essentially by the hurler on the ground, which is going to be the same as the force applied by the ground. So once again, we're write down our equation for the impulse, force times time, is equal to change in momentum, right? So the final momentum, there's only really one subject here of hurdle. So the final momentum is going to be mass times the final velocity minus initial momentum, which is going to be mass minus initial velocity. And we really know all these quantities already. So, right, we know initial, we know final velocity, we know the mass, we know the time. So we just have to find this one unknown of force. So F is equal to mv final minus mv initial, divide both sides by time, plug in our values for mass and for initial and final velocities, the time, and we'll find that the force is equal to 600. We have 3 6s, lucky number, and that's going to be our final force, right? Okay, great, guys. In the next video, we're going to go over a very important example that will have to do with applying impulse to graph related questions. So I would highly advise you watch this if you want to succeed in this unit. And of course, the most important part, guys, is to practice these questions on your own. Keep practicing and keep watching these videos on your way to an A. Thank you.